system classification. Now let's look at a circuit with a capacitor. Okay, this is a simple circuit with a current flowing. Here the current is I of t, and here's a capacitor, and the capacitor is C of C. So the voltage output is going to be VC, that is voltage across this capacitor, that is VC of t. Then here we have plus minus, and here the input is I of t, and the output is VC of t. Okay, so you know that if you have a simple circuit like this, we can write the equation for the circuit by using this formula. VC of t is equal to 1 over C integration negative infinity to t I of tau d tau. Okay, this is the equation for voltage when it's related to a capacitor. Now here we are going to analyze the type of system that's going to have this equation. Like first we want to see whether this is a memoryless system. To find out whether this is a memoryless, we have to look at the definition of memoryless. The memoryless definition is given by output of time t, output at time t at time t depends on input at time t and all past inputs. Okay, so it basically says the output of time t should be depending on time t alone into all past inputs. But the thing is, here this is not the case, because at time t we are getting VC of t, but there's a time you can take negative infinity to time t. There are time in between, not only the time t's, right? So it's not just depending on time t. So therefore this is not a memoryless. If it always time t, then this is memoryless. If it's depending on various different of time, then this is not a memoryless. So this system is not memoryless. Now if it satisfies this, then it's going to satisfy the causal. Now let's look at the definition for the causal system. Let's write the equation again. VC of t is equal to 1 over C integration negative infinity to t I of tau d tau. And here let's look at the definition for the causal system. Causal system is defined by output at time t depends on input at time t and all past inputs. Okay, I made a mistake here. this is output of time t. It depends on input at time t, not all the past inputs. If it all the past inputs, that's a causal. Okay, so this one, but here the case is depends on all the past input as well. Like negative infinity to t, there's a lot of time in between, so that depends on that as well. Therefore, this system is causal. Now let's look at whether this is a linear system or not. To find out whether this is a linear system, we can do a check and see if it's satisfying the superposition. Is it holding the superposition at the end? So to check the linear, what we can do is we let I of t is equal to alpha 1 I1 of t plus alpha 2 I2 of t, and I1 of t should give the output of y1 of t, and then I2 of t should give the output of y2 of t. Let's see if that happens. So if I take the function y of t and 1 over c, integration negative infinity to t, and instead of I of t I substitute this one. This is alpha 1 I1 of t plus alpha 2 I2 of, okay, let's put tau here because that's the one we have. Because the time is starting from negative infinity to t, so all the time should be applied. So that's why we use a different variable for it. So I1 of tau I1 of tau d tau. Let's continue this one here. So this one, I can substitute this 1 over c for both of them and separate this one as separate equation. So we can simplify this one, like alpha 1, here we are integrating this one with respect to tau. So this is a constant value, so I can take that one to the front as well. So this is going to be alpha 1 in front, and then 1 over c, and then integration negative infinity to t, and then I1 of tau. Okay, d tau, and I write the other equation as alpha 2 is a constant, and then 1 over c, integration negative infinity to t, and then I2 of tau d tau. I just write these two as separate, like two different equations. You can do that when you have these things in a bracket. So now let's compare this one with the function. Like you can see this almost like this function right here, like until this is a function, right? So we can call this one, this whole thing except this alpha 1 as a y1 of t, and we can call this exact thing as y2 of t. So from this one you can see, go and continue to the next page. Y of t is equal to alpha 1 y1 of t and plus alpha 2 y2 of t. So you can see this system is a linear system. System is linear. Okay, so this is that, And let's see whether this system is a time invariant. Let's write the equation again. Y of t is equal to Vc of t, that is equal to 1 over c integration negative infinity to t I of tau d tau. Okay, to check whether the system is time invariant, what we can do is we can do a time delay. Like for example, if I do the current time delay by t minus t naught, you subtract, that's a time delay. If you apply that, that should gives the output of y1 of t, and that y1 of t does we have to check whether that y1 of t is equal to y of t minus t naught. If that is true, then this is time invariant system. Now to check that, we apply this. So y1 of t 1 over c negative infinity to t. Here we do a time delay I of tau minus t naught and then d tau. Now to integrate this one, what we can do is we can let lambda, we introduce a new variable that is equal to tau minus t naught. If lambda is tau minus t naught, then d lambda is going to be the d tau. Okay, so let's substitute that and do the integration. 1 over c negative infinity and then t minus t naught here, and then I lambda. Okay, lambda d lambda. So this is gonna give the output of y of t minus t naught. That's what we want to prove. Like, does y1 is equal to y of t minus t naught? Yes. Therefore, this is system is time invariant. Okay, that is this. And then now the last thing we are going to check is this system is a bounded input output system. Okay, is this system is bounded input output system, BIBOS is stable, BIBOS stable. So to check that, let I of t u of t, because u of t is the bounded input. So if we input u of t and if we get an output that is also a bounded output, then this is a bounded input bounded output stable system. So we are going to apply u of t instead of I of t to check whether it will happen. So a bound input, u of t is a bound input, unit step function. Now let's look at the example. Y of t 1 over c integration negative infinity to t, and then instead of I of tau, I'm going to put u of tau, because we want to input a bounded input in order to see if it's giving a bounded output. If it gives, then it's a bounded input output stable. If it's not giving, then this is not a bounded input output stable system. So here I'm applying u of tau instead of I of tau, and then d tau. And if I do that, 1 over c integration negative, and the unit step function start from 0, so we don't need negative infinity and all the stuff. So we can start from 0 right here, and then t, and then u of tau d tau. And if you integrate a unit step function, that is a ramp function, r of t. So 1 over c r of t, this will be the output if you integrate this. So from this one we can see that this is like r of t ramp function doesn't have a bound. It grows without a bound. So when the when the numbers time goes to the positive, t approaches infinity, it goes to infinity without any bound. So this is not a bypass system. This is not bypass stable system, because we are not giving a bounded output as a result. The output is not bound, so not bypass stable. And that's how we can analyze system based on the circuit or equation given using these methods. I hope you guys find this video helpful. Thanks for watching. Don't forget to subscribe my channel. See you in my next